A quick method of numerical differentiation based on MATLAB arrays. So in calculus, we define the derivative of some function f of x based on the change in f over some change in x for ever decreasingly sized steps in the x direction. As you probably remember, for polynomials and some other stuff, it's fairly easy to find derivatives. But when you start getting into more complicated mathematical functions, this could be very tough to calculate analytically. So let's think about this for a second. As delta x gets smaller, we get closer and closer to this analytical derivative as delta x goes towards 0. But for practical purposes, there is some small but non-zero delta x that we can consider close enough that any further reduction in delta x doesn't increase the accuracy of the derivative towards the analytical solution by any meaningful amount. Okay, that's what I mean when we say we're close enough. We're close enough that the error between taking the limit as delta x goes to 0 and not taking that limit by leaving delta x as some non-zero, some finite step, the error between those two derivatives is negligible. So let's think in computational terms, in numerical terms. Let x be an array, x1 through x sub n, and let's let some function of x also be an array. Call it f1 through f sub n. Then we could approximate the derivative of x with respect to, or of f with respect to x as an array as well by taking the difference between sequential points in the x and f of x arrays. You can see at x1 and f1, the derivative can be approximated as the difference between f2 and f1 over the difference between x2 and x1. Okay. Basically breaking down that derivative we saw on the previous slide into a series of steps based on a finite collection of x and f of x values. This is a forward difference approximation. We're looking at the difference between a point and the next point in line in the array to calculate the derivative. And this leads to a little bit of a goofiness in that the derivative we calculate, the first point in the derivative array that we calculate, is more accurately the derivative between the first 2 points in the x and f of x arrays. Maybe this will make more sense graphically if we had a red line representing f of x across some span of f1, f2, f3, x1 through 3, then we can see the approximation of df dx1 and df dx2 is not really following the tangent lines, which we know represent the derivative at x2 and x1. They're more shifted to be between the values. Okay, and so the forward difference doesn't quite work when we need to know the derivative at x1, at x2, at x3. It's giving us the derivative between x1, x2, and x3, and so on to however many values we run this. So we see a difference in the slopes of the tangent lines and our approximation lines. We can fix this to some extent. We can get a much better approximation of the derivative, for example, at x2 by using what's called a central difference, by looking both forward from x2 towards x3 and backwards x3 or x2 back to x1. And graphically, we can see a derivative at x2 based on the central difference, looking forwards and backwards simultaneously towards 3 and back towards 1, gives us a line that, at least qualitatively, we could say is much closer in slope to the tangent line we can observe at x2, which means the central difference does a lot better at approximating the derivative at the points of interest in our arrays. Okay, so we could define the central difference at some point n as the difference between the function f at n plus 1 and the function f at n minus 1 divided by the difference of x at n plus 1 back to x minus 1. Okay, and this is a better agreement than the forward difference does between the numerical and the numerical approximation and the analytical solution. But with the central difference, we run into trouble, particularly at x1. At the initial point, we can't look backwards from x1. We don't know what's going on. There is no x0. And at the ending point, xn, we can't look forwards. There is no xn plus 1 if you're at the last element in x. There are many ways around this, but a reasonable and very quick approximation adjustment. It doesn't provide quite as good of accuracy as the difference between, or as the central difference does, but we can use a forward difference alone at x1, and we can use a backward difference alone at xn, with everything from 2 to n minus 1 being calculated by the central difference method. And this will give us a derivative array with decent approximations at the endpoints and really good approximations at the midpoints. There are added steps we can use to make these endpoints a little bit better, but this is a very good, quick first approximation when we'll leave it here. Let's put this into MATLAB. So given some array x, given some array f of x, you can see I've used x is 1 through 10, and f of x is the natural log of x. But it can be any arbitrary x and f of x arrays. We will initialize our df dx array as a collection of zeros to start with, and we want to fill that in. Let's use the central difference for the middle points. So df dx from point 2 to the point before the end of df dx. That can be done by a central difference where we start, if we look at the first element df dx, that is at the second point, df dx2, we want f of x3 minus f of x1 over x3 minus x1. And at the second to last point in df dx, we want f of x at the end over f minus f of x at third to the end, or n minus 2, over x at the end minus x at the n minus 2. So although this array notation takes a little bit of wrapping your head around, it's a very quick way to calculate that central difference. And then for the first and last elements in df dx, we want to fill those in using the forward and backward difference approximations respectively. Put it all together, these 4 lines of code calculating df dx can work to give you a decent approximation for most purposes of arrays of x and f of x. If the array notation gets you a little bit mixed up, a for loop can be used. But as you'll learn, if you start working with larger and larger arrays, the array method, the array notation, is far faster from a computational perspective. And once you get the hang of it, it's not too much more difficult than writing out a for loop, and in many cases is actually far more concise. And again, you could put in any arbitrary x and f of x arrays. So have fun. I'm sure your calculus teacher won't appreciate the quick approximation here, but for engineering purposes, this can often get you close enough.